Welcome back to Rock the JVM, folks. This is Daniel, and in this video I'm going to start talking about ZIO Streams, which is a cool little library for the ZIO effect system. So in this video I'm going to assume that you're obviously comfortable with the Scala language and you have some essential ZIO knowledge, which I teach in the ZIO course here at Rock the JVM. Obviously, if you want to write code with me, this will be the most effective use of your time watching this video, and whenever you need to refresh your memory, just refer back to the video or to the written form at the blog, which you can find in the link description, and it also contains detailed explanations of everything that we are going to discuss in this video, which is probably going to be a little long, and I might split this into multiple videos, but all the content can also be found in written form with detailed explanations at the blog. Alright, now we need a good definition of what streams are because we have a good intuitions of what they are, but we don't have it formally stated. So for the purpose of this video, a stream is a potentially infinite sequence of elements that will become available over time, maybe from different systems. And this definition is pretty broad, and it's used for different purposes in the classical data streaming tools that we have in the Scala ecosystem. So as examples of streams, we have the stream which became lazy list in Scala 2.13 and then Scala 3. This is a collection of elements that are lazily evaluated once. Then we have very complicated tools such as Kafka, Pulsar, or RabbitMQ, which are message buses, where data elements are written into some append-only log to be read later by some consumers. And these tools fit our definitions of a stream because the messages that arrive in Kafka, Pulsar, RabbitMQ, or tools of that sort can also be potentially infinite, and they become available over time depending on which systems write to them. Now, streams can also be used for data processing, which is why Spark Streaming and Flink are also potential examples of streams. We also have tools for functional programming such as FS2 and ZIO Streams, which is the subject of this video, where elements are pulled and handled when available, again, potentially infinite sequences of these elements or messages. And likewise, Akka Streams is an equivalent tool for processing infinite collections of elements, but these elements arrive asynchronously and they're handled in different parts of an application with back pressure and a variety of other features. So in this video, I'm going to show you ZIO Streams, of course, the components that build ZIO Streams, how to run them, how to handle errors, and finally at the end of the video, I'm going to show you an example of how to use ZIO Streams to inject tags into some markdown fictitious blog posts. Alright, so let me get back to my development environment. I'm of course running IntelliJ IDEA here, and I've added ZIO and ZIO Streams in my build.sbt. You can find the library definitions in the blog post if you want to check them out. So ZIO Streams, of course, they're both at ZIO 2.0, and ZIO JSON, which is a library that's being developed, so we're going to treat JSONs in this video. We're going to import ZIO JSON a little bit later. I'm going to actually import that ZIO JSON everything so that we have it ready, and we're going to import a variety of other types as we go through the examples. Now, if you want to learn more about ZIO, I've just launched, literally a couple of weeks ago, a course on ZIO 2.0. So if you want to check that out, I also left a link in the description. This was pretty much my hottest course for the year. Anyway, so let me show you the components of ZIO Streams. So we have the fundamental data type, which is a ZStream. And a ZStream is a source of data that can be potentially infinite. I'm going to start with something simple. So let me define a stream as a ZStream, and ZStreams have the same type arguments as regular ZIOs. You probably know about ZIOs themselves. ZIO effects are descriptions of computations that might fail with some exception, that require some dependencies, and that might succeed with a actual value. So effects, we have a success as a ZIO of, and we define a val. So a ZIO with the type arguments, let's say any, which means no requirements, nothing, meaning it cannot fail, and it can succeed with an integer, and I can use ZIO.succeed with the value 42, of course. This is the fundamental effect type. So ZIO is an effect that can describe any sort of computations with potential side effects. The first type argument means dependencies or environments, so this is the kind of value that the ZIO will need to be able to be run. The second type argument is the error type, which is the type that the effect might fail with, and this can be a throwable, but it can also be a string, an int, or any kind of thing that might mean an error to you, so this is pretty flexible. And the third type argument is the success, the desired value of this effect when it's being evaluated. And when I say ZIO.succeed42, this is just a data structure that when evaluated will produce the value 42. And the evaluation of ZIOs will be performed in the run method at the ZIO app default. So my object extends a ZIO built-in type, which is ZIO app default, which will evaluate a single effect, which might spin up the world for all it cares. But this run method is just your entry point, which will create all the ZIO data structures and evaluate those. So that was a whirlwind tour of what ZIO offers. I'm pretty sure you know more than that. So the ZIO streams are defined by this ZStream with the same type arguments with the same meanings. So I'm going to have a ZStream of any, nothing, and int, meaning that this ZStream doesn't have any dependencies, it cannot fail, and it produces elements of type int. So the ZStream can produce zero or more elements of type int. So I'm going to say ZStream dot from iterable, and I can pass any regular Scala collection like 1 to 10, and this will produce all the elements from 1 to 10. Of course, this is just a description of all the numbers 1 to 10, but from iterable will force this range to be evaluated one by one. If I define, let's call this inStream, again as a ZStream of any, nothing, and int, you can also pass a variable number of arguments to a ZStream. So a ZStream has a companion apply method. So a ZStream where you can say 1, 2, 3, 4, 5, 6, 7, and 8, for example. Of course, you can pass any number of arguments as you want. So a ZStream is a collection, I'm going to put collection in quotes, of 0 or more, potentially infinite, elements. And you can map these, so I'm going to say let's call this string stream, as a ZStream of any, nothing, and string by running some regular map transformations on a ZStream. So I can say, for example, inStream.map, and I can say _.toString, and this changes the type of elements being produced. So you can map all these elements as they arrive and convert them to whatever your business logic requires. So this ZStream is a quote-unquote collection. In fact, it's a source of 0 or more elements. Now, this ZStream can be plugged into sinks. So a sink is a destination of your elements. So you can do something with the elements and maybe return a meaningful value. Now the sink will have a very different type signature with more type arguments. So for example, if you want to sum up all the elements of a potential source that produces elements of type int, I'm going to define a val called sum, and this is going to be a ZSync. And notice that the ZSync has 5 type arguments. This is pretty nuts. So I'm going to describe what those type arguments are. The first is the environment, much like a ZStream or a ZIO. The error type, in this case, nothing. The elements that are going to be processed, which are integers. So we have the first 3 that signify the same things as ZStreams or ZIOs, but the ZSync has 2 more type arguments. I'm going to use nothing and int, meaning the leftover values. Now this ZSync data type has the fundamental meaning that you may or may not consume all the elements in your stream, which is why the 4th type argument describes the leftover element types, which in this case is nothing because we want to consume all of them. So by specifying the type argument nothing, you clearly guarantee the fact that you're going to consume the entire stream. And the 5th type argument is the so-called materialized value. This is the Akka streams equivalent that this sync might return after processing all the elements that it has. So in this case, I'm going to have a ZSync.sum with the type int, and this relies on some implicits to be able to do that. So ZSync.sum consumes all the elements in the stream and returns a value of type int. This is what it means. So you may not necessarily need all the data, so I'm going to give you some examples of ZSyncs that may not consume everything. So let's say take 5. Take 5 as a ZSync of, and I'm going to have any nothing because I don't care about the environment or the error type. We're going to deal with errors a little bit later. The element types that are going to feed into this sync are going to be int, and let's say that I want to leftover ints, So I'm not going to consume all the elements in the stream, so all the elements that are left are going to be of type int, and I want to return what is called a chunk of int. A chunk is a data structure built into ZIO, which is kind of an array, which is a highly optimized, effectful array value. So I want to take just the first 5 elements out of a stream, so I'm going to have ZSync.take5, and this will return a ZSync of this type. Now you can also process the output type into maybe a different type, so maybe you want to do something with these integers once you've acquired them. So I'm going to have, let's call this take5 map, and I'm going to copy most of this type signature, but this is going to be a ZSync with any nothing int, so the first 3 type arguments are going to be left intact. The 4th type argument is going to be left intact as well because I'm only going to use take5, but the chunk here I'm going to process them as strings, for instance. So after I've taken the first 5 elements, I might want to turn them into strings as saying take5.map, and I can use the chunk as the argument, and I'm going to do a chunk.map internally, so I'm going to say _toString. So chunk is this array-like data structure that has the kind of methods that you would expect for such a collection. So after you've acquired all these integers that you care about, you can turn them into something else by running some business logic on top of them. In this case, I've run something very simple. Now, for leftovers, meaning the elements that you haven't processed, given by this 4th type argument, you can do something with them so that you don't leave them over and maybe do something with them in the sync. So I'm going to say, let's call this take5, let's call this leftovers. And this is going to be a ZSync of any nothing int, and I'm going to use nothing here because I want to consume all these elements and return them in the return time, the output type. So I'm going to have a chunk int and chunk int, and I'm going to use take5.collect leftover. And collect leftover gives you the possibility of dealing with the chunk int that you haven't processed in the original stream. So maybe you want to do something with them outside the core business logic in your application. Now, to identify which chunk int is the leftover and which chunk int is the output, the first one is the output, and the second one is the leftover. Let me use take5 map to make this a little bit clearer, and I'm going to have chunk string here. So let me add a little annotation. So these are the output, and these are the leftovers. Now, technically, this whole tuple is the output type, but every member of this tuple means something else. So if you want to collect all the leftover values and do something with them, you can collect leftover with this little method, or you can ignore them. So you can say val take5 ignore as a ZSync of any nothing int chunk int and turn the 4th type argument into nothing. You can say take5.ignore leftover. Now, there is a very interesting method called contramap. And contramap allows a sync which is typed with a particular type, such as take5, to be operated on a source that is a ZStream of a different type, giving a mapping function from the original element to the element that the sync will require. So for example, if you wanted to run StringStream, which is a ZStream that produces strings, on take5, which consumes ints, that would be quite impossible unless there is a mapping function from string to int. And we can define, let's call this take5 strings, and this is going to be a ZSync of any nothing string, and then return int and chunk int as the leftover and the output type respectively as take5.contramap, and I'm going to use _.toInt. And this will assume that this lambda will be applied to every string consumed by this sync. And this allows it to be connected with a ZStream that produces strings. And in the end, you'll produce ints, of course, and the leftovers will be of type int, and the output type will also be chunk of int. So this is a map function that will be applied to all the string elements that will come its way, but it's called contramap because we run this lambda, or we pass this lambda as the argument to the sync, not to the eventual source that will be connected to the sync. Now, contramap is a little bit less intuitive, so I'm going to show you a very beautiful ASCII diagram. I'm going to have a ZStream that produces strings, and I'm going to simply pass a type argument in this pseudo scala. And this can be connected to a ZSync of int.contramap, and you can pass a lambda here. Or you can connect a ZStream of string, and then you can pass the map with the same lambda, so map on that lambda, and connect that to a ZSync of int. So you can think of a contramap as the map function that will be eventually applied to the ZStream that will be connected to that sync. So this connection is the same as this other connection. Now, speaking of connections, you can connect a ZStream with a sync and return an effect. So I'm going to have a ZIO as, let's say we want to put all the ints here into the sum sync. So I'm going to have a ZIO that I'm going to pass the int stream, and I'm going to say run with sum. And this will produce a ZIO effect. So this will be a ZIO of any nothing. Of course, it's a ZIO of any nothing, and it will produce the so-called materialized value of this little sync. I like to call it materialized value because it connects more easily to the ZIO Streams terminology if you use that as well. So this is the final value that will be produced by the sync, which will be the final value produced by the effect when it's being evaluated. Of course, if I do in main ZIO.debug, I'm going to print the value produced by this ZIO when it's evaluated. And of course, the run method evaluates that. So if I run this application, we're going to see the sum of the first 8 numbers here in this in stream. All right. Right, so we have 36, which is obviously the first 8 numbers summed together. All right. So when you connect a stream with a sync, you get an effect which produces or requires all the dependencies of both, produces the lowest common ancestor of all the error types of these two, and produces, when evaluated, the desired value or the output type of the sync. All right. Cool. Now, speaking of connections, ZStreams are more than just ZStreams to syncs and then calling the run method, of course. You have what is called processors, or in the ZIO Streams terminology, that's called a ZPipeline. A ZPipeline is a transformer or a processor of elements in between a source and a sync. So I'm going to show you how to use ZPipelines. Let's call this business logic. And of course, in practice, this may be quite involved. I'm going to have a ZPipeline. And the ZPipeline has 4 type arguments. First is the environment type, then you have the error type, and then you have 2 value types. Let's say that we want to transform strings into ints. So we're going to have the string type, which is the input type, and the output type is going to be int. So you push strings one way and you get ints the other way. So I'm going to have a ZPipeline dot map, and I'm going to have underscore dot to int. So, for example, if you have a stream of strings that are numerical in nature and you want to transform them to ints and then sum them together, you can have, let's call this ZIO version 2 as, again, a ZIO of any nothing and int. You can have the string stream, and then you can say via this business logic, and then run with the sum sync. So the string stream via business logic gives you a composite source that produces ints, because the business logic will transform the strings from the string stream into ints, and then you can push those ints into the sync, which will sum them together. Now, of course, you can add many pipelines, not just one, so not just source via pipeline to sync, but you can add many pipelines. So for instance, if you want to process these strings, transform them to ints, and then just filter those that are, for example, just even numbers, you can say, let's call this filter logic as a ZPipeline, and we have any nothing, and then you can have, let's say, int to int. So you get ints one way, and you push ints the other way. And I can use ZPipeline dot filter, and I can say underscore mod2 must be equal to 0. So only those even elements will be pushed downstream. Now you can connect the business logic with the filter logic and contain, let's call this app logic, as a ZPipeline of any nothing, you receive strings one end and you push ints the other way by considering this map transformation and the filter transformation by using business logic and run this little transformer, let's call this go-to or something like that, with filter logic. So business logic and then filter logic, or feeds into filter logic. And you can pass this app logic to the string stream. So you can say, let's call this ZIO version 3, again as a ZIO of any nothing, and it produces one int. And you can say string stream dot via this app logic, and then run with the sum sync. And again, this will run the sum on only those elements which are even. So if I do ZIO version 3 debug, we should get half of that, 36. Because we have 20. So we only have just the even numbers. So 2, 4, 6, and 8. Obviously, that sums up to 20. But this is an example of how you can combine pipelines together and obtain one potentially giant stream here by this little expression. All right, so this was a quick introduction to ZIO Streams. In the next video, I'm going to show you error handling with streams, and after that, I'm going to give you a realistic scenario with ZIO Streams. If you like this video, go ahead and click the like button for me and subscribe to the channel for more videos like this. And check out the Rock the JVM website and the ZIO course, which I've left in the description if you're interested in using ZIO. Until next time, folks, I'm Daniel, signing off.